Hello everybody, this is Dr. Sergey Sargasov, and let us talk about the countability, okay, so can we count, right? Let me explain that, countability of the rational numbers, okay? Let's talk about that. So the countability of the rational number set, right, numbers. And what are the rational numbers? By the way, remember, the rational numbers are represented by the letter Q, like this. Okay, let me do this. Q, with a little kind of vertical line there, bolded Q. And this is my students, and I taught them, I said, what is this Q for? And they said, quickly, what if it's probably for quotient, right? Division of two numbers. And so, what in the world is a rational number? First, we have to understand that a rational number, okay, what is a rational number? It's a number represented by, let's say, it's a set of numbers, okay, let's put numbers, represented by m over n, okay, where m and n are integers, okay, m and are integers, they're belonging in the set, the z set, the integer set. This is Zentrum, that's why the z, that's what I studied that the central numbers, basically the Germanic word Zentrum, that's why z there. And so that bolded z, so m and n are integers, okay, such that, okay, they are relatively prime, okay, meaning that m, the GCD, let's say the GCD of m and n equals 1. So they're already simplified reduced fraction, right? So rational number is basically a fraction, okay? And, okay, n cannot equal to 0, right? We're not going to divide by 0. We're going to forbid that, okay? And so that is a set of rational numbers, in other words, fractions. We're talking about, look, what I said is countability, right? Now, what in the world is countability? Well, countability, okay, let's think about it this way. What are counting numbers? Another word for counting numbers, okay, I tell my students that this is another word, there's something called natural numbers. And natural numbers and counting numbers are the same set of numbers. Some people don't know the word counting numbers is actually also used instead of natural sometimes. But the set of counting, okay, counting numbers, and the same as natural, okay, natural, let's see, numbers. These are given by that bolded n for natural, right? And this is just 1 to the positive integers. 1, 2, 3, not even 0. Okay, 1, 2, 3, 4, 5, 6, and so on and so forth, right? And the idea being there's a first element, there's a second element, a third one, a fourth one, a fifth one, a sixth one. You can count them from 1 to, whatever, and on and on and on. Okay, that's what counting natural numbers are. So natural numbers are countable. Okay, does that make sense? Natural numbers are countable, right? So this means that natural numbers, these numbers, okay, and of course they're counting numbers also, those numbers are what we call countable, okay? And remember I said, hey, let's show that the rational numbers are countable. Well, to some of us it may seem obvious, like seemingly so, that yeah, obviously, the first, second, third, like fractions, they go on and on, get bigger and bigger. Or some of us are like, wow, really? That doesn't make sense at all, because think about it. On the top you can have any integer, and on the bottom you can have any integer. It's like an infinity, right? Like kind of one of these divided by another infinity. That's like infinity squared. Like what in the world, right? What do we do with that? And so I'm just giving you kind of a simplified version of the argument, but let me show you. Cantor was a gentleman in history of mathematics that studied countability of numbers and in general the cardinality of numbers quite a bit, okay? And he was kind of given this credit for finding this Cantor's argument for why the rational numbers, again, the rational numbers, all these fractions, they're also countable. In other words, there's a first one, you can call it like this is a fraction 1, this is fraction 2, this is fraction 3, fraction 4, fraction 5, fraction 6. And if you do that, you can still get all of the fractions that ever you can imagine, okay? So let me show you how we can do that, okay? What we can do is, okay, we say, 1, 2, 3, 4, 5, 6, 7, yeah, those are countable, right? The first, second, third, fourth, fifth, and so on. Now, what I'm going to do, this kind of the argument, the basic one that I know, okay, this Cantor argument, is let us go ahead and do a little table, okay? So let's do this. Let's kind of draw a little diagram. Okay, let's see. Let's do this. So a little table here, okay, with numbers, okay, and we're going to do countable, like we're going to do natural numbers. Let me show you what I mean by that. So we're like, all right, let's talk about the natural numbers. 1, okay, 2, 3, 4, 5, 6, so forth, so on and so forth. And this, what about this? 1, 2. We're going to do 1 by 2 by, the kind of the natural numbers by the natural numbers. That would make sense, right? That fractions, rational numbers, they're, positive integers are natural numbers over natural numbers, and they can be negative or positive, by the way, right? So look, 4, 5, 6, and so on and so forth, right? And the quick question that I have for you is, would you be able to see right away, let's kind of do on a side note, would you be able to see that integers could be made, maybe this is a good example to start with, that integers could be made also proven to be countable. This is easier of an argument than rational numbers. So let's think of it this way, okay? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, right? These are the natural or the counting numbers. They're obviously countable. The first, the second, the third number is 3, the fourth number is 4, and so on. Now, the integers, to show they're countable, what you can do is you can say, you know what, let me just begin with 0. And let me go to 1, and then, plus or minus, so minus 1. And then let's go to 2, and then minus 2. And then 3, and minus 3. And then 4, and minus 4. And then 5, and minus 5, right? And in fact, when you have an integer 2k here, a natural number 2k, you will have the integer k. And when you have 2k plus 1, you will have a negative k, okay, and so on, right? That's the idea. So you can see it's a mapping, okay? It's a one-to-one and onto mapping. And that's the idea of what a set of, why this set is also countable, just like basically this one is by the definition of what countability is, okay? First, second, third, and fourth. So you can say, you know what? The first integer is 0, and the second one is 1, and the third one is negative 1. And of course, you could do another ordering on it, but this is an order we can give to prove that, yes, they are countable. Okay, well, rational numbers, what do we do here? Well, it's trickier, much trickier. And so there are other arguments, okay, but this is the one that is kind of considered to be the common one that most people really relate to, Cantor's argument. Let's do this. Let's say this is kind of the M column, the left. On the left is M, and on the right is N. Okay. And remember, what is a rational number? An m over n, an integer over an integer, right? And by the way, I'm already doing positive, right? We can do plus or minus. So we'll put the plus or minus in as well. But look, let's just do the positive rational numbers for now. Then we'll do the negative and the 0 as well included. So the positive rational numbers, in fact, let's call these, let me show you, we can call these, let's move this all this down a little bit. And the positive rational numbers, we'll call them, let's talk about with the Q plus. Okay, that's a way to kind of denote positive rational numbers. That's one way to do that. So again, numbers that are rational fractions, but just the positive ones, because obviously we're here doing positive integers. But, natural numbers here, not even 0 anywhere. So here goes. We can say, you know what? Let's do m over n. 1 over 1 is 1. Then we have, look, let's go by row. 1 over 2, right? And then, so we go, let me do this. Let's do this out. This is usually the way it's done. You go like this. And then you go, look, what's 2 over 1? What's 1 over 2? What's this? 2 over 2? That's just a 1, right? This, and this. So let's just fill in these blanks. Look at this. 1 over 3, 1 over 4, right? I'm doing always this number over one of these. 1 over 5 here, right? See, 1 over 5. So row by column would be m over n. 1 over 6. This would be what? 2 over 1, 2 over 2, 2 over 3, 2 over 4. Let me just keep it this way. It's 2 over 4 is 1/2, of course. 2 over 5, 2 over 6. And you see, you can repeat them. They'll be repeating. This is not a really one-to-one and onto argument, but this still will show the countability. And this is 3, 4, 5, 6 are divided by 1. This is divided by 2, so 3 halves, 4 halves, 5 halves, 6 halves, right? And so on and so forth. And this was what? 3 over 3. Let me just keep it as 3 over 3, not 1. 3 over 4, 3 over 5, 3 over 6, and then this is what? 4 over 3, 4 over 4, 4 over 5, 4 over 6, and this is what? 5 over 3, and this is 6 over 3, and this is 5 over 4, and this is 6 over 4, 5 over 5, and 6 over 5. And so, of course, you get more and more numbers, obviously, right? You have 5 over 6 here, 6 over 6 there, and some of them are really repeating. This is just a 1. It's the same thing we already had here. But what we can do is we can say, you know, let's make a trail with the following. Let's go, this is the first number, okay, that one. And then we go second number, let's go diagonals. Second number, second rational number, third rational number. And then we go diagonal, this one, fourth, fifth, sixth, okay, seventh, eighth, ninth, 10th. And this is a weird order, but do you see how all, if you do it this way, first, second, third, fourth, fifth, sixth, if you do it this way, all these diagonals will take care of all positive rational numbers. Of course, many of them will be repeated so many times. Look, here's a 1, 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 right? 6 over 6, 5 over 5, and all that, 4 over 4, 3 over 3. They're all the same. But the idea being that if you do this 1, 2, 3, 4, 5, if you by this diagonal approach, right, you will actually take care of, there's no rational number that will be left behind that is a positive rational number, right? You see, like, think about it. Like, what about like a 5/6? Well, there it is. What about a 5/4? There it is. What about a 6/5? There it is. What about a 1/3? We already did that, right? What about a 7/2? Well, 7/2 will be right over here, right? So we can always make any in this, and this, all these numbers are taken care of in this way. That's the whole point that I'm trying to show you. This is the argument that takes care of the fact that even though you're repeating them, there is such a thing as, and what we can do is if it's been used, we just don't use it again. But we go in these diagonals and we basically 1, 2, 3, 4, 5, 6, 7 corresponds to the first, the second, the third, the fourth, the fifth, and so on rational numbers, the positive ones for now, right? And so let's do this. Let's actually write them out as what were they? They were let's do this with this color, a little thicker here. So 1, 2, 1/2, right? That's what we had. 1, 2, 1/2. That was how we're going diagonal. See that? 1, and then oops, and then we have 2, and then 1/2, and then we get 3, 1, 1/3, right? 3, 1, 1/3. Let me get rid of this. So 3, 1, 1/3. And again, this is just an idea. One, you know, we already did 1, right? So we don't do it. So 1/3. Okay. And then we have 4, 3/2, 2/3, 1/4. These are all new numbers. 4. What was it? 3/2, 2/3, 1/4, right? And then we have, what is it? And there's even an argument you can give to whichever number that is. That's a little tougher, I think, the function, the actual number that you get, f of k is what, right? Because like if you put a 9 here, to get that it's a 1/4 is a little trickier to just me tell you, oh, you know, it's a -1 divided by 2 and flip that. It's not that easy because, of course, you have to understand we're going to be skipping a lot of numbers, for example, that we already used again. Like 1 we use here and we use here, so I'm not going to write 1 again. It's a little trickier. I encourage you to try to find a function that actually does that. But so 1/4, and then we have 5, and then we already have the, see, that's a 2, we already did that. That's a 1, we already did that. That's a 1/2, we already did that. So 5 and then 1/5, right? And so 5 and 1/5, right? And then on and on and on. And then, of course, if you want to do all, right, all rational numbers, you can say, okay, let's do this. Let's do, first of all, just put a 0 in for the first number, 0, right? We have to take 0 somehow. And then you see the 1, let's do 1 minus 1, right? And then you see 2, let's do 2 minus 2. And you see 1/2, let's do 1/2 minus 1/2. So let's do everything plus minus for everything we see. But there's still, this is going to be the first, the second, the third, the fourth, the fifth, the sixth, the seventh. And that order will take care of, as you understand now, all rational numbers. And that's the idea. And so the countability is that it's still that infinity of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. It's going in that infinite, the cardinality being, right, the that cardinality of the natural numbers. It's the mega, I believe, cardinality. So anyway, 1/2, we have the 3 and then negative 3, right? I'm just doing plus or minus this, and then plus or minus 1/3, so 1/3, negative 1/3, and then we can see what would be after that. You can do a 4, negative 4, and a 3/2, negative 3/2, and just so on and so forth, right? I mean, that's the idea. Okay, this is one way to really understand why the rational numbers, the fractions, all the fractions can be basically made first, second, third, like countable, like just like integers.